Hello, Math 101. Justin Pashar here once again. Welcome to our next class. We begin chapter 6 today. I hope everybody is doing healthy and well and staying safe and sane during this pandemic. But we're almost there. We're almost there with the course. There really is light at the end of the tunnel. I just want to say I think everybody's doing a very nice job getting the work in on time and learning this material. I know it's not easy doing this at home, believe me, it's not. And today we'll embark on a new chapter. And I think the good news here is a lot of these things you have been exposed to in high school for the most part, but I'm going to try to break this down for you as much as I could, but not get too long on this topic. Try to keep it short and sweet for you guys being in 101. However, with these topics we're going to learn, we could spend an awful lot of time if we really wanted to, but we're not going to do that. We're just going to kind of get the basics. So in this video, we're going to look at section 6.1, which is titled Real Numbers, Order, and Absolute Value. And what I'm going to attempt to do here in this first video is kind of construct the real number system a little bit for you guys. Some of these things will be familiar. I'm going to kind of go through the way the notes is set up a little bit, but I'll stray a little bit off those too because you can read the notes on your own. But what we want to do is essentially construct the real numbers. So the real numbers, we usually abbreviate with a capital R. It looks like this, a scripted R. Of course, you don't have to draw your R to look that way. But what I want you to think of it is like this. The real numbers, think of it as a big giant box of numbers. Of course, we can't fit every single number that exists in the box, right? Because the box is finite. But think of the real number system as a giant box. And what we're going to do is we're going to put smaller boxes into it. So these smaller boxes are going to make up this giant box of numbers. And the first small box of numbers that we're going to put into the reals is the natural numbers, which is given by capital N. And you've seen this capital N before. That was in the last chapter, number theory. N stands for the natural numbers. So the natural numbers are a very nice set. These are the counting numbers, 1, 2, 3, and so on. Once again, it is an infinite set. So we have the natural numbers. Now I'm going to kind of draw a number line up here. We all know what a number line is. It's a way to concretely classify numbers on a line in some kind of order, which we'll talk about later. But natural numbers would be these points here, like 1, 2, 3, so on, right? You know, we could put 4 here if we want to, and that would go on forever in that direction, of course. But natural numbers, 1, 2, 3, 4, equal distance between each of them on the number line. The natural numbers are a good set of numbers. However, they can't do everything for us, and that's why mathematicians always had to create more sets of numbers. So another set of numbers we have is the whole numbers, and we use W. And the whole numbers are the natural numbers plus 0. So the set looks like 0, 1, 2, 3, and so on to infinity. So it's another infinite set. The whole numbers contain the natural numbers plus 0. So we could actually think of this in terms of a subset. Everything in N is also in W. So that gives us this special number 0, which we'll put right here on the number line. There it is, 0. Very special number. In fact, many civilizations mathematically didn't know what to do with 0. They knew there had to be some kind of number that showed an absence of number. But I believe it really was the Mayans. I think those were the first mathematicians, the first people to come up with the idea of 0, conceptualize it. So the whole numbers are very good, right? Because, for example, in the natural numbers, if we did like 3 minus 3, we'd get 0. 0 is not contained in the naturals. But now in the whole numbers, we have that possibility. If something's going to be subtracted and get a 0, now we have a set that supports it. So the whole numbers are good, but they have their limitations too, of course. So we have another set of numbers called the integers. And we use a capital Z for integer. It comes from the German word for integer. And the integers are everything that the whole numbers are, plus their opposites. So for instance, here's 0, 1, 2, and 3. Those are definitely integers, but also -1, -2, -3, and so on to the left. So integers are positive and negative whole numbers. So those would be numbers like -1, -2, -3, and so on. Those are the integers. And these are the numbers that you probably had to fit with. I know I had trouble in 6th, 7th grade with these types of numbers, trying to add them, like -3 plus a -5 or -3 plus 2. All those wacky signs. So those are integers, these numbers right here. So now it brings us, think about we're filling this box, right? So we have the natural numbers, they're contained inside the whole numbers. The whole numbers are all contained inside the integers. So we're filling all these boxes into this big box of numbers. And now we get a really big box of numbers inside called rational numbers. And we use Q to denote the set of rational numbers because rational stands for quotient. And quotient means you divide. So what does this set look like? Well, there's many ways we could write it, so I'll show you one way. It's the set of all numbers x, such that x looks like a over b, where a and b come from the integers, and b cannot be 0. So I know that's kind of a mouthful there, right? But this is how we write it using set builders. The set of all numbers x, so your number x belongs to Q if it looks like this, a over b, where a and b come from the integers. So essentially, how do we get rational numbers? We take integers and we divide them, and that's how we get this set. With the exception that b cannot be 0. We cannot divide anything by 0, so those things will not be included in the set. And you know that already from school, elementary and high school. Now, in turn, what always makes this a little bit of a slippery topic is the fact that fractions could also be written as decimals. So we also have to include Q is the set of all terminating and repeating decimals. So it's also the set of all terminating and repeating decimals. And in section 6.3, we talked specifically about what's in Q. But for example, here are some examples of things that would be inside Q. The number 1/2, right? Because 1/2 also could be written as 0.5, and that's what we call a terminating decimal. -1/2, which is -0.5, that's still rational. The number 2, for example, would be considered rational because we could write that as 2 over 1, and as a decimal, 2.0. A number like 1/3, right? You guys know this. 1/3 is 0.3 repeating. So if you go in your calculator and do 1 divided by 3, you'll see that's going to be 0.333 forever. So this is what we call a repeating decimal, but this is still rational. As is something like 2/3. Now 2/3 is 0.6 repeating, and just like here, we put that bar over top of the 6 to indicate that that digit goes on forever. Now here's an interesting thing that you probably already know, however. Your calculator is going to lie to you because in most calculators, if you do 2 divided by 3, it's going to say 0.6666, and in the very last spot, it's going to put a 7. So you're going to think, oh, well, 2/3 is 0.67. It isn't. That's what your calculator is doing to round up. The calculator always tries to round up if it can. In any case, 2/3 is 0.6 repeating, and this thing is a rational number. Something that would not be rational would be like the number pi, because that's an approximation of 3.14. Those decimals go on forever, and they fluctuate and jump all over the place. And we don't know what the last digit ever will be. I don't think anybody will ever tell us what that is. But in any case, these are rational numbers. Okay? Now, what this could do, by the way, for our number line is now we have the ability to put numbers in between. So we could put a 1/2 in between 0 and 1. We could put 1 1/2 between 1 and 2, and we can place all these decimals in between. And it brings us to an interesting point that we'll talk about soon, which is called density, meaning how many numbers are there actually between other numbers. Very interesting topic. You could spend years on that as well. Now, we have natural numbers, whole numbers, integers, rational numbers. Now, there's another set of numbers called the irrational numbers, and we use I for that. And what does this set look like? It's the set of all x where x is not in Q. That's the easiest way to write this. And what it means is an irrational number is one that is not terminating and not repeating. So, for example, I, the square root of 2. If you put the square root of 2 in your calculator and get a decimal, that thing jumps all over the place. This is considered irrational. The number e, that's irrational. Something like the opposite of square root of 13 or the square root of 21. All these would be considered irrational because they have decimals that don't terminate and they don't repeat. So oftentimes people think that these aren't real numbers. They are still considered real numbers. They're just not related to any of these. So in other words, if you're one of these types of numbers, you can never be one of these numbers. And if you're one of these numbers, you can never be one of these. However, all of these numbers make up the real numbers. So if you imagine this as a giant box of real numbers, as you can see, all the numbers over here would be considered rational numbers, Q. And inside that, you have natural numbers. Inside that, you have whole numbers. Inside that, you have integers. And in turn, all these guys belong to Q. So, how do you think of the real numbers? Well, think of the real numbers as an addition sentence, essentially. You could think of it as rational numbers plus irrational numbers. The irrationals would be over here. And then how do we write this in terms of our set theory stuff? Well, the real numbers is the union between rational and irrational. So it's the real numbers is Q in union with I. And that's the whole main idea, essentially, for us in 101, is that the real numbers could be summed up as the addition or the union of rational and irrational numbers. I always thought this topic was weird when I was in school because nobody ever really explained it to me. Then when I went to college and I studied this stuff more extensively, it really opened your eyes to how things work. And we're going to go more in detail on this, of course, later, but this is the basic idea. And what we could also gather from this is subset relations. So, for example, we could say that the natural numbers are a subset of the whole numbers, which are a subset of the integers, which are a subset of the rational numbers, which in turn is a subset of the real numbers. And the irrational numbers are a subset also of the real numbers. Even though they don't have anything in common with Q, Z, W, or N, the irrational numbers I, they still are a subset of real numbers because we could put those as approximations on the number line. For example, pi is 3.14. We could mark a point there, call it pi, somewhere between 3 and 4 if we wish. So they still are considered real. As I always tell like my high school students, the irrational numbers, you could think of them as like the weirdos of the real number system because of their idea that their decimals flip and flop all over the place. Okay? So those are your sets that we're going to work with. And this diagram you'll see in your lecture notes, this is kind of helpful to help you realize that if you're a natural number, you're also a whole number, you're also an integer, you're also rational, and of course, you're real. Beyond this course, you're going to learn about the complex numbers. And you can think of this whole big box of real numbers being dumped into another big box called complex numbers. But that's beyond this class here. You'll learn that in intermediate algebra, college algebra, pre-calc, and of course calc. Okay, so this is a good place, I think, to pause the video, go back and look at some of this stuff, and then we'll just talk to you about a few more things And that'll be the end of this video. Okay, so I hope you're able to absorb a little bit of that. So we could talk about sets like we did in the beginning of the year. For example, we worried about how do we take a union or an intersection. We could do the same thing here with these infinite sets. So here's some examples. Say we want to take the natural numbers and we want to union that with the integers. So it's just easy when we had concrete sets with a finite number of numbers. But how do we take a union and intersection over infinite sets? Well, these are more basic ones. There's a lot more complicated ideas out there than these, but this could be complicated enough for some people. I would draw a picture to get started. So think of the natural numbers. Here's a number line. And let's put the natural numbers on there. You have 1, 2, 3, and so on. And then down here is the integers. So there is 1, 2, and 3. But the integers also have things like 0, -1, -2, -3, and so on, right? So if you take the union, that means you want to take both sets and put all their elements together. So what is this set going to look like? Well, it's going to feature all of the natural numbers, but it's also going to feature all of these negative numbers that the naturals don't have. So when you union the natural numbers with the integers, you get the bigger of the two sets, which is the integers. So the trick here is, if you look at two of these infinite sets, if you want the union, you take the bigger of the two sets as the answer. And conceptually, I think we would agree that there's more things in the integers than there are in than the natural numbers, okay? We could also do this the other way. We could say, how about the natural numbers, we want to intersect them with the integers. So now remember what intersection means. Tight lid, right? So what do they only have in common? Well, we could think of it as a one-to-one matching. For example, they would share all the things to the left of 3, right? 4, 5, 6, 7, 8, 4, 5, 6, 7, 8. So we could think of this as a constant one-to-one matching. So they both have 3 in common. They also have 2 in common. They have 1 in common. But what happens here? You get to 0 on the integers, there's no natural numbers left. So if you want the intersection, they have to be the things that they have in common. They don't have anything in common now to the left of 1. So the intersection is going to be the smaller of the two sets, which would be the natural numbers. And that's how that works. So when you take the intersection of two infinite sets, generally you're looking for the smaller of the two sets conceptually, and that will be your answer for the intersection. So again, I would urge you to pause the video at this point, kind of think about this idea. Look in the lecture notes because I give you several other examples using some other sets. And then I have one more idea we'll talk about that's kind of related to this, and then we'll mention absolute value. Something that we know to be true is that the real numbers is what we call dense. And what dense means is the fact that between any two real numbers, so if we have a real number A and a real number B, we could always find another number C that's real that's between them. So the real numbers are considered dense. And we could go actually further and say the rational numbers are clearly dense, right? So if you have a rational number A and a rational number B, you can always find some number C that's in between them. For example, let's say we have the rational number of 0 and 1. Well, what's a number that's between 0 and 1? Well, 1/2 is a perfect candidate, right? The idea that it's dense means that this continues forever, of course. So what if we looked at 0 and 1/2? What's a number that's between 0 and 1/2? Can we find another rational number that's between 0 and 1/2? And we can. For instance, we could take a 4th. And then we could continue this pattern forever. What's another rational number between 0 and a 4th? Well, how about something like 1/16, for example, right? We'll get small. And we could keep going. Between 0 and a 16th, we might have 1/32. And we can continue this process forever. That's why we call this density. So the real numbers are dense. The rational numbers are dense. But a good thought question that you might have is, are all these sets we talked about dense? For example, are the natural numbers dense? How about the integers? Are they dense? Some of the results may surprise you, but this is a good question to think about. So in your spare time here, think about, are the natural numbers dense? Would the integers be dense? And maybe we'll talk about that in the future. Remember, for dense, it means that between any two of those numbers, we could always find another one of those. So if you want to ask, are the natural numbers dense? There better be another natural number always in between. So that's density. The last topic then is absolute value. And that's something you should know. Now, one of the great fallacies is that some teachers will say absolute value is always positive. Well, it is positive, but not always. Because the absolute value of 0, for example, is 0, and 0 is neither positive or negative. So absolute value, what is that exactly? It's the distance from a number x to 0 on the number line. That's what absolute value is without using all the notations. So for example, what's the absolute value of -5? Well, how many spots away is -5 from 0 on the number line? It is 5 spots away. We always measure distance in terms of positive numbers. What's the absolute value of 5? Well, that's still 5, because 5 is 0 spots away, and 5 is 5 spots away from 0 on the number line. So that's what it means to have absolute value. And there are certain things we could do. Like we could simplify absolute values. Like say we have something like the absolute value of 2 minus 5. Right? So we perform the operation on the inside. 2 minus 5 would be -3. And what's the absolute value of -3? +3. So we could perform arithmetic with absolute value. Now, if you have something like this, let's say we have the absolute value of 2 minus 5, and we have a minus out in front of it. You can never distribute a minus through the absolute value. That's illegal. So you take care of the absolute value stuff first. 2 minus 5 is -3. What's the absolute value of -3? That's +3. Then we just apply the minus sign that was floating out in front. So you see how if you put a minus out in front, it changes your answer. So those are a couple of examples of absolute value. But I'm pretty sure most of you guys are familiar with this idea. Okay? So that'll end this first video. This pretty much covers the stuff that you see in section 6.1. I will do another video shortly on 6.2, which is properties of real numbers and order of operations. So I hope this video is going to help you a little bit. You know, I understand, once again, it's hard to learn this stuff at home. Believe me, I can understand. But I do appreciate the effort. And as always, if you have any questions on homework or material, please feel free to call or email. Other than that, I'll see you on the next video. And until then, stay safe, stay healthy, and I'll see you when I see you.